Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1984 witnessed not solely the dystopian narratives of George Orwell, but moreover, a profound advancement in understanding the fundamental forces governing the universe. This essay undertakes a detailed examination of the scientific publications elucidating the discovery of the W and Z bosons, a breakthrough awarded the 1984 Nobel Prize in Physics to Carlo Rubbia and Simon van der Meer. We shall evaluate the internal claims presented within their seminal works, dissecting the arguments, scrutinizing the evidence, and assessing the methodologies employed in this monumental achievement. This exposition will offer a comprehensive critical analysis aimed at experts in physics, history of science, and advanced undergraduates, revealing the intricacies of the experimental process and theoretical framework that underpinned this landmark discovery. Section 1 Introduction. The Standard Model and the Quest for Intermediate Vector Bosons. The discovery of the W and Z bosons constitutes a cornerstone of the Standard Model of particle physics. This model, a comprehensive framework for understanding the fundamental constituents of matter and their interactions, posits that these interactions are mediated by force-carrying particles, known as bosons. Electromagnetism is mediated by the photon, a massless particle that transmits electromagnetic forces. However, the weak nuclear force, responsible for radioactive decay and other processes, was theorized to require massive intermediary particles. These hypothetical particles, dubbed the W and Z bosons, were predicted to exist with specific properties, including substantial mass, a parameter that explained the short-range nature of the weak force. The experimental confirmation of their existence, described in detail in the publications under scrutiny, provided crucial verification for the Standard Model and opened new avenues for exploring fundamental physics. Prior to the experiments led by Rubbia and van der Meer at the European Organization for Nuclear Research, or CERN, direct observation of the W and Z bosons remained elusive, presenting a significant challenge to the scientific community. Section 2. The super-proton synchrotron and stochastic cooling. Realizing the ambitious goal of discovering the W and Z particles required a significant leap in accelerator technology. The key innovation enabling the experiment was the transformation of CERN superproton synchrotron, or SBS, into a proton-antiproton collider. This collision of matter and antimatter at extremely high energies provided the necessary conditions for the production of the rare and massive W and Z bosons. Van der Meer's development of stochastic cooling was absolutely fundamental. Stochastic cooling is an ingenious technique to increase the density of antiproton beams. Antiprotons, being antimatter, are challenging to produce and accumulate in sufficient quantities. Stochastic cooling addresses this issue by actively reducing the random motion of particles within the beam, thereby concentrating the beam's density and increasing the likelihood of collisions. The process operates on the principle of detecting statistical fluctuations in the beam's density and applying corrected impulses to individual particles, dampening their transverse and longitudinal oscillations. The specific implementation involved utilizing pickup electrodes to sense the beam's position and kicker electrodes to apply correcting forces, guided by sophisticated electronic feedback systems. The technical papers detailing stochastic cooling meticulously outline the mathematical formalism governing the process, including the derivation of equations describing the damping rate and the limitations imposed by noise and bandwidth constraints. The claim is that this novel approach permitted the effective accumulation of antiprotons at a density sufficient for high luminosity proton-antiproton collisions, the crucial prerequisite for the W and Z boson discovery. This claim is supported internally by the detailed performance metrics of the SBS collider after the implementation of stochastic cooling, demonstrating a substantial increase in luminosity, a measure of the collision Section 3. The UA1 detector, a comprehensive instrumentation approach to detect the elusive decay products of the W and Z bosons amidst the high-energy debris of proton-antiproton collisions. The collaboration constructed the UA1 detector, a massive multipurpose apparatus designed to capture a wide range of particle signatures. The central detector element was a large drift chamber system, meticulously described in technical publications, designed to track charged particle trajectories and measure their momenta. This involved filling a large volume with a carefully chosen gas mixture and applying a strong magnetic field, causing charged particles to curve along helical paths. By precisely measuring the curvature of these tracks, the detector enabled determination of the particles' momenta. Surrounding the central detector were electromagnetic and hadronic calorimeters, designed to measure the energy of particles that interact electromagnetically or through the strong force. These calorimeters were constructed using alternating layers of absorber material, typically lead or iron, and scintillator material, which emits light when struck by charged particles. The amount of light produced is proportional to the energy deposited by the particle. Detailed documentation covers the calibration procedures employed to ensure accurate energy measurements, accounting for variations in scintillator response and detector geometry. The UA1 detector also incorporated muon detectors, designed to identify muons, heavy cousins of the electron that penetrate deeply through matter. These detectors were placed outside the calorimeters, shielded from most other particles. The claim made in the original publications is that the UA1 detector's comprehensive instrumentation, covering nearly the entire solid angle around the collision point, provided optimal sensitivity for detecting the decay products of the W and Z bosons, enabling unambiguous identification of these particles through their characteristic decay signatures. This performance claim is underpinned by the detailed descriptions of detect performance parameters, including momentum resolution, energy resolution, particle identification efficiency, derived from extensive simulations and calibrations. Section 4W boson discovery identifying the leptonic decay channel. One of the key signatures used to identify the W boson was its decay into a charged lepton, specifically an electron or a muon, and a neutrino. Neutrinos, notoriously elusive particles that interact very weakly with matter, are undetectable directly. Their presence, however, can be inferred from the apparent imbalance of momentum in the detector, the missing transverse energy. The publications describe the meticulous selection criteria applied to the data collected by the UA1 detector to isolate events consistent with this decay signature. The process involved identifying events with a high-energy electron or muon, well isolated from other particles, and a significant amount of missing transverse energy. Stringent cuts were applied to variables such as the lepton's transverse momentum, the missing transverse energy, and the angular separation between the lepton and the missing energy direction. The claim is that after applying these selection criteria, a clear excess of events remained above the expected background, originating primarily from known processes such as quantum cryptodynamic jet production, with subsequent misidentification of jets as leptons. The publications provide detailed estimates of the background contributions derived from Monte Carlo simulations and data control samples. The observed distribution of transverse mass, a kinematic variable calculated from the lepton momentum and missing transverse energy, exhibited a clear peak around 80 gigaelectronvolts per the speed of light squared, consistent with the predicted mass of the W boson. This observation, coupled with the estimated background levels and the shape of the transverse mass distribution, provided compelling evidence for the discovery of the W boson, a key claim of the original publication. Section 5Z, boson discovery confirmation through diplepton decay. The Z boson, being electrically neutral, can decay into a pair of charged leptons, either electrons or muons. The publications describe the identification of Z boson events through the observation of these dilepton decay channels. The selection criteria for Z boson events was similar to those used for W bosons, but with the requirement of 2 high-energy leptons instead of 1, the invariant mass of the dilepton pair, calculated from the momenta of the 2 leptons, is expected to cluster around the mass of the Z boson. The publications present the observed distribution of dilepton invariant mass, exhibiting a clear peak centered at approximately 9 to 1 gigaelectronvolts per the speed of light squared, consistent with theoretical predictions. The observed width of the peak is primarily determined by the detector resolution, a factor carefully accounted for in the analysis. The major background contribution to the dilepton signal comes from the Drell-Yan process, the production of lepton pairs through quark-antiquark annihilation. Accurate estimation of this background is critical for establishing the significance of the Z boson signal. The papers detail the techniques used to estimate the Drell-Yan background, including normalizing Monte Carlo simulations to the observed data at invariant masses away from the Z boson peak. The observed number of events in the Z boson peak, after subtracting the estimated background, establishes a clear signal, providing strong evidence for the existence of the Z boson from an invariant mass perspective. The observation of both electron and muon decay channels with consistent results further strengthens the Section 6 mass determination and standard model consistency. Accurate determination of the W and Z boson masses is crucial for testing the standard model. The publications outline the methods used to extract the mass values from the experimental data. For the W boson, the mass is primarily determined from the transverse mass distribution, which is less sensitive to the longitudinal momentum of the W boson. The analysis involves fitting the observed transverse mass distribution to a theoretical template, taking into account detector resolution and background contributions. For the Z boson, the mass is determined from the invariant mass distribution of the dilepton pairs. The fitting procedure includes corrections for radiative effects, such as the emission of photons from the leptons, which can distort the shape of the invariant mass spectrum. The publications present the measured values of the W and Z boson masses, along with their associated statistical and systematic uncertainties. These uncertainties arise from various sources, including detector calibration, background estimation, and theoretical modeling of the signal and background processes. The obtained masses, when compared with precise measurements of the electroweak mixing angle, are shown to be consistent with the standard model predictions, providing further validation of the model's internal consistency and predictive. Section 7 Production cross-sections and theoretical agreement. Furthermore, the publications address the production cross-section of the W and Z bosons, a measure of the probability of producing these particles in proton-antiproton collisions. The measurement of the production cross-section involves counting the number of observed events, correcting for detector acceptance and efficiency, and normalizing by the integrated luminosity of the collider. The theoretical predictions for the production cross-sections are based on perturbative quantum cladodynamics, or QCD, which describes the strong interactions between quarks and gluons. The publications compare the measured production cross-sections with the theoretical predictions, finding reasonable agreement within the experimental and theoretical uncertainties. Discrepancies between the measured and predicted values can provide hints for new physics beyond the standard model, motivating further theoretical and experimental investigations. Therefore, precise determination of their production cross-sections are important. Section 8 Analysis of transverse momentum distributions. The papers dedicate attention to the transverse momentum distributions of the W and Z bosons. These distributions provide insights into the dynamics of the underlying parton interactions that produced the bosons. Perturbative QCD predicts that the W and Z bosons should acquire transverse momentum from the emission of gluons by the colliding quarks. The shape of the transverse momentum distribution depends on the strong coupling constant into the parton distribution functions, which describe the momentum distribution of quarks and gluons inside the proton and antiproton. The publications present the measured transverse momentum distributions and compare them with theoretical predictions. The agreement is generally good, or some discrepancies are observed at high transverse momenta potentially indicating the need for more sophisticated theoretical calculations or the presence of additional contributions from beyond the standard. Section 9. Systematic uncertainties and data validation. The meticulous consideration of systematic uncertainties is a hallmark of these publications. These uncertainties reflect imperfections in the detector calibration, background subtraction, and theoretical modeling. The papers dedicate extensive sections to quantifying and propagating these systematic errors. For example, the uncertainty in the integrated luminosity, which directly affects the measurement of the production cross-sections, is carefully evaluated based on the stability of the beam monitoring system and the accuracy of the luminosity calibration procedures. The uncertainty in the detector energy scale, which affects the mass measurements, is assessed by studying the response of the detector to known particles with well-defined energies. The publications demonstrate significant efforts to validate the data and ensure the robustness of the results. Control samples of known physics processes are used to verify the detector performance and the analysis procedures. Consistency checks are performed by comparing results obtained using different decay channels and different analysis techniques. Section 10. Impact on the standard model and future directions. The discovery of the W and Z bosons, as meticulously documented in these publications, has had a profound impact on the standard model. It provided crucial confirmation of the electroweak theory, unifying the electromagnetic and weak forces. The precise measurements of the W and Z boson masses and couplings have constrained the parameters of the standard model and have opened new avenues for searching for new physics. The discovery also paved the way for future experiments at higher energy colliders, such as the Large Hadron Collider, which have extended the standard model and explored new frontiers in particle physics. The original publications conclude by highlighting the ongoing efforts to refine the measurements of the W and Z boson properties and to search for other predicted particles, such as the Higgs boson, which was eventually discovered in 2012. In essence, the legacy of the 1984 publications extends far beyond the immediate discovery, shaping the course of particle physics research for decades to come. Section 11. Critiques, revisions, and the evolution of understanding. The initial reception of the W and Z boson discoveries was overwhelmingly positive, though some critiques and refinements emerged in subsequent years. Certain analyses questioned the initial estimates of background contributions in specific decay channels, prompting a re-evaluation of selection criteria and background modeling techniques. Specifically, the identification of W bosons decaying into tau leptons, a heavier version of the electron and muon, presented significant challenges due to the complex decay modes of the tau. Initial analyses may have overestimated the signal significance in this channel, leading to revisions in the published results. Furthermore, the precision of the W boson mass measurement was limited by systematic uncertainties related to the detector energy scale. Subsequent experiments, with improved detector calibration and higher statistics, have reduced these uncertainties and provided more precise measurements of the W boson mass. Continued refinement of theoretical calculations of the production cross-sections, incorporating higher-order QCD corrections, has further improved the agreement between theory and experiment. These critiques and revisions, far from invalidating the original discovery, have contributed to a deeper and more nuanced understanding of the W and Z boson properties and the intricacies of high-energy collider physics. Section 12. The broader scientific context and technological legacy. The discovery of the W and Z bosons did not occur in a vacuum. Rather, it was the culmination of decades of theoretical and experimental progress in particle physics. The theoretical framework of the electroweak theory, developed by Sheldon Glashow, Abdus Salam, and Stephen Weinberg in the 1960s, provided the theoretical foundation for predicting the existence and properties of these particles. The experimental confirmation of their existence, however, required a significant leap in accelerator and detector technology exemplified by van der Meer's stochastic cooling and the UA1 detector. The legacy of this technological innovation extends far beyond the W and Z boson discovery, impacting the design and operation of subsequent high-energy colliders. Stochastic cooling, with its ingenious feedback mechanism, has become a standard technique for improving the performance of particle beams. The multipurpose detector concept, pioneered by the UA1 collaboration, has been adopted by numerous experiments, enabling comprehensive studies of particle interactions. Moreover, the data analysis techniques, developed and refined during the W and Z boson analysis, have become integral to the toolbox of particle physicists. The scientific and technological legacy of the 1984 publications continues to shape the field of high-energy physics. In conclusion, the publications surrounding the discovery of the W and Z bosons represent a monumental achievement in experimental particle physics. A meticulous evaluation of their claims, methodologies, and evidence reveals the rigor and ingenuity that underpinned this discovery. The development of stochastic cooling, the construction of the UA1 detector, and the sophisticated data analysis techniques all contributed to the successful identification and characterization of these fundamental particles. While subsequent research has refined certain aspects of the original analysis, the core findings remain valid and represent a cornerstone of the standard model. The enduring significance of this work lies not solely in the discovery itself, but moreover in the technological advancements and intellectual insights that it spurred, shaping the trajectory of particle physics research for generations of scientists. The discovery has had a lasting impact on the way particles are observed and understood.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.